Are we recording? Yes. Okay. So we're going to revisit the Boolean operations, but we're going to view them with a different notation. Okay. So this comes from engineering. Okay. We're going to see the notion of logic gate, which are used to create the bigger circuits, right? So these are all put together to create circuits. Okay, so from chapter 4, right, we interpreted false and true as 0 and 1. And if you remember so that was at the very end of chapter 4, we saw that we could interpret and or almost like product and plus, right? I said min and max, which is the same thing. So min and max is the same as and or when you look at them as 0 and 1. The and is the same as the product. So we talked about that very briefly. So if you look at the and, of course, it's the same as multiplying. So 0 times 0, 0 times anything is 0, and 1 times 1 is 1. The or is almost like a plus, right? So 0 plus 0 is 0, 0 plus 1, 1 plus 0 is 1. The only one that doesn't work is 1 plus 1, because there's no 2, right? XOR was also a way of interpreting sort of like a plus. But we're not going to deal with XOR here as a connective or logic gate directly. So we're just going to use and, or, and negation, okay? So here is the notation, which comes, this is a very old notation, comes from the engineers. So the Boolean variables, we will use small or lowercase letters, such as X, Y, Z. Prime will be used for negation. Okay, star will be used for and. I'll get back to that in just a sec. So you think of it as this is the product. It's really the same as product, and we'll use plus for or. Okay, so even though it's not really a plus because there's no 2, but in this context, we'll use the plus. Okay, so here are the tables for these 3 basic operations on 0 and 1. Okay, and as usual for the product, we'll, instead of writing x star y, we'll just write xy. Okay, and if you think again in terms of zeros and ones, this makes perfect sense, right? 0 times 0 is 0, and so on and so forth. Okay, all right, so using this, we can build bigger expressions. So these are called Boolean expressions. So these are expressions which are built correctly from Boolean variables and these 3 operations, prime, product, and plus. Okay, so here are some basic examples. X plus x prime, this is a Boolean expression. XYZ prime plus x plus y prime u, this is also a Boolean expression. And here's a more complicated one. So we've got x, y prime, z prime plus y, all that primed, plus x prime z, and all that primed. Okay, sorry, and so forth and so on. Okay, so let's see an example with the full table of values here. So you see that I'm using 3 variables here. My expression is x, y, z prime plus x. Okay, so if I evaluate x, y, z prime at 0, 0, 0, well, it's immediate, right? This goes very fast. There's x is 0, so when you multiply through, this whole thing is 0. 0 plus 0 is 0, and so forth and so on, right? So if you look at maybe not the last one, just the one before. So x, y, z, the values are 1, 1, 0 over here, right? So then it means that x, y, z prime will be 1 times 1 times 1. 0 prime is 1. So you do get a 1 here, plus 1, and that's 1, right? So this plus here is the special plus. 1 plus 1 is 1, which looks silly out of context, but In this context, that's what it is, okay? All right, so again, this is just same as or and not, just different notation, different way of writing them, okay? Now here is a important result, okay? And I will explain this. I'll spend a little time on this. So the theorem states that every Boolean expression is equivalent to another Boolean expression, which is what we call a complete sum of products form. And this form is actually unique. Okay, so let's explain everything in this statement. So by equivalent, we mean, as we talked about last time, as in logical equivalence, it's the same truth table. So our two Boolean expressions have exactly the same table. So it's this different ways of writing the same expression, if you want, the same circuit. Okay. What's a sum of products? Well, like the name says, it's a sum of products. So if you go back to the examples that I've shown, they were not all sums of products. I had primes around big brackets. So these are not sums of products. So a sum of product is like a polynomial written in standard form. So we have monomials, which are just products of variables or primed variables, and you add those up, okay? Another way of naming this, if you're using the logic notation with or and, is this is called DNF, disjunctive normal form. I won't go there, but if you've seen this before, that's the same thing, okay? The complete part, this is maybe the not so obvious part. So let's talk about this. So up to now, what we're saying is that you can take any Boolean expression and you can rewrite it as a sum of products, which if you think a little bit about it, I mean, you might believe this, right? The complete part, this is the trickier part here, but that's what makes this whole thing unique. The form is unique. It's because of that completeness. So what do we mean by complete? It means that every one of those products contains every variable, okay? So the trick is this. So suppose, and I'll show you several examples as we go along, is that suppose that there's a variable missing in a product. Then what you can do is you can tweak it as follows. So here's the basic trick. So look at x plus x prime. Just think about x plus x prime. What is the value of that? So if x is 0, this is 0 plus 1, which is 1, okay? If x is 1, this is 1 plus 0, which is again 1. So x plus x prime is always 1, right? And 1 times p is just the same as p. So I can replace any product p by x plus x prime p. And it turns out, and I haven't said this earlier, that the distributive law works nicely here. So x plus x prime p is the same as x times p plus x prime p. So if you have a sum of stuff and there's one of those products p, there's no x in it, then you can actually just do this little trick to replace your expression and you'll get x appearing that was missing, okay? I'll show you some more concrete examples very soon, okay? So every Boolean expression is equivalent to a sum of products, which is complete, and this form is unique, okay? And in fact, using this trick, and I'm going to show you, probably not today, because it's going to be a little bit too much, but on Thursday, I'm going to show you that with this idea, this is something I mentioned last week, that any truth table can be realized as some Boolean expression, okay? And I'm going to try to convince you of this. Okay. circuits. So now there's another standard notation that if you've ever done anything that has to do with electronics, and you have probably seen this notation for gates, logic gates, which are elementary circuits from which bigger circuits are built. Okay, so I'm going to show you the basic notation for these circuits, and I'm going to show you for at least two of those the way that it's realized physically, and it makes sense. You'll see it makes a lot of sense. Okay, so this is basically how you realize these physically. Okay, yeah, so as I was saying, standard notation for all of that. Okay, so let's go with our first gate, the OR gate, right? So that's the plus, right? So here we wrote A plus B equals to Y. So we have all the possible values for A and B. And that's that little thing that looks like a Star Trek crest. That's the notation for the OR gate. Okay, so when you see that, if you have a circuit which is drawn and you see that thing there, it means that it's an OR gate. Okay, so that's very standard. So how do you physically realize this thing with actual wires? This is actually pretty easy. So here's how you would do this. So you have this, so on top I have the notation for the circuit. At the bottom is the actual, if you wish, realization of the circuits. We have a lamp, and the lamp lights up means that it's 1. The value on input A and B is 1, and if it doesn't light up, then the output is 0. Okay, there's a battery and there's a lamp, and of course you probably know that if you want the lamp to light up, the circuit has to be closed. So how do you close this circuit? Well, you can either close at A, right? You can close this thing is like a little door. You can close it here, so this will close the circuit and the lamp will open up, will light up. Or you can close B and the circuit will be closed and the lamp will light up. So that's how you realize an OR gate. So either close A, or close B, and the circuit will be closed. Okay? So that's the physical realization of an OR gate. So that's sort of, you could almost do that, in your basement, an OR gate. All right. What about the AND gate? So this is what we denote as product, right? Or the AND. So it's 1 precisely when both inputs are 1. This is the notation for the AND gate. So it's a straight part and curved on this side. And how do you realize this? So both have to be, think of in terms of those doors. If you want the lamp to light up, both should be closed. So what you do is you put them one after another, right? So you have your battery, you have your lamp. So the lamp will light up, 1, when both are closed. If you close only one of them, it's not going to light up. The circuit will still be open. So to close the circuit, you want to close both of these, and then this thing will light up. Okay, so that's, you could physically realize this this way. Okay, so you see, you can, I'm not actually showing you circuits inside a machine, obviously, but you see that in theory, you could actually build these things and put them all together if you had enough room to do it. So the first computers were somehow built in this way, right? Okay, last one, the NOT gate, the notation for the NOT, so there's only one input, obviously A prime. And so this is the notation for the NOT gate. It's a little triangle with a little round part here. This is used using resistors. It's a bit trickier to actually realize physically. So I will not go there. Sorry, my mouth is rusty. Confinement, wonderful. Okay, so let's move on. Yeah, more inputs, that's the notation, right? So you can, you these operations are associative, so you can have more inputs, then there's no problem. So what's the OR of 4 inputs, right? As long that's clear, right? As long as one of the inputs is 1, it'll light up as 1, right? And if they're all 0, it'll be 0. For the AND, let's say here we have an AND here with 3 inputs, right? For this to light up, all 3 have to be 1, right? So we extend our notation and the concept of these gates to more than 2 inputs, right? The NOT is always 1 input though, okay? Yeah, so this is what I was saying. So because the operations are associative, there's no problem in doing this, right? You could physically you'd plug several of these gates one into another, right? That's how you do it. Okay, yeah. So here is another bit of notation. So how does a machine a circuit work, right? So when you need a clock, right? Because you have several inputs coming in and you have a circuit, but it can only treat at any single fixed time. It has to treat just one input for each input wire, right? So you have a clock, and that's why each tick of the clock you have values coming in, values coming out. Then there's another click of the clock, and then this goes right one after another. So you're treating several inputs sequentially, one after another. Okay, so how we write that down is rather than look at single bits, we look at sequences of bits, right? Or bit strings, if you wish. And we're going to write down how these gates or circuits treat the bits coordinate-wise. We discussed this last week, right? So for example, the or the plus, right? So if I have sequences of bits coming in, so A would be 11000110, and B would be the sequence 10010101. Then what is the output of the OR gate here? Well, it's just coordinate wise. So you take the plus of each bits in each position of A and B, right? So there's nothing. So for example, here is 1 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, and so on, right? Okay, which brings us to the notion of special sequences. Okay, so last week I talked about a method to make sure that when you're writing down a table, that you have all the possible values for true and false. Here is another way of doing it, which is smart, which is, turns out it's exactly the same thing, but it's a different approach, which might suit you better if you prefer this, okay? So I'm talking about it here because, well, it's an alternative to what I talked about last week, and in the book, there are some exercises that deal specifically with special sequences. So let's talk about that. So I have a Boolean expression or circuit or gate, and I want to write down its truth table. So I want to make sure that I have all possible inputs, right? So as we talked about last time. So you can if with the sequential inputs notation, we can list all the possible inputs. Okay, what are special sequences is the way of remembering, if you wish, how to write all possible values. So these are sequences of zeros and ones which alternate between 0 and 1 at different rates. Okay, so here is a first example. So I have the gate the Boolean expression a plus b. Okay, so two variables. So you think there must be four possibilities. So here's a way of writing down all the possibilities. Notice that our truth tables were written vertically. This is horizontally, but it's exactly the same thing, right? So look at the values of for A. So you have two zeros and then two ones. And then for B, you have zeros and ones, but they alternate twice as fast. So we have 0, 1, 0, 1. Okay? And if you put them one on top of another, you'll see that you get every single possibility that you need. So 0, 0, 0, 1, 1, 0, 1, 1. And then you can write down the values for the output. Okay? So to better see what's going on, let's do one with three variables. Okay? So let's say that I have some Boolean expression y, which involves three variables, a, b, and c. Okay, so I want to write down all possible inputs for y. So what I do is this. For a, I'll write the sequence which has 4 zeros and then 4 ones. Okay, for b, I'll start alternating twice as fast. So I have 0, 0, 1, 1, 0, 0, 1, 1. And then for C, it alternates twice as fast, 0, 1, 0, 1, 0, 1, 0, 1. And if you look at the columns, you will see that this will produce every single, all the different inputs to Y that you need, right? You have 8 of them. 3 variables, 2 power 3 is 8, okay? So if you had 4 variables, then you need 4 sequences. So 8 zeros, 8 ones, that would be your first sequence, and then 4 zeros, 4 ones, 4 zeros, 4 ones, and then you alternate twice as fast and twice as fast, and you'll get all the possibilities this way, okay? Now, if you look at the resulting table, it's exactly the same that what I described last week, but it's just a different way of thinking about it, okay? So these are what are called special sequences. Okay, all right, circuits. Here's a picture of a circuit. I took this from the book, and there's a typo in the book. Be careful. I don't remember which example it was, but there is the equivalent in the book has a typo in it. Okay, so let's take a look at this picture. It has 3 inputs, A, B, C. It has 1 output, Y here, okay? So you see that you have wires going into this AND gate. The little dots here means that you have a branching, so your wire goes also into another AND gate, another AND gate here. There are negations on these wires, and then wires coming out. The outputs of these AND gates are going to this OR gate, and that's your output, okay? So I'd like to obviously write down a Boolean expression for this circuit, okay? So let's see what this looks like. Well, so this is an AND, and A, B, C are going in there, so that's A, B, C. The second one here, I've got A, the negation of B, and C, so that's A, B prime, C. And this one here has negation of A and B going in, A prime, B, and Y is the OR of all these 3 products. So this is the resulting Boolean expression for this circuit. So you see this is a sum of products, as we discussed, by the way. Okay, so circuits don't have to be written this way, but that's an example of a sum of products. Okay. Now, it is not complete, right? So we talked about this. We said every circuit can be written as a Boolean expression, which is a sum of products, which is complete. This one is not complete. You see that the last product is missing C or C prime, depending, okay? So we could make it complete if we wanted to. I don't know if let's see, did I? Okay, I'll get back to that. Okay, so anyway, let's write down the truth table for this circuit. So I've got my Boolean expression. I want to know what this circuit does, right? So let's write down the truth table. So I have 3 variables. That means 8 possibilities. If you want to use special sequences, there you go. 4 zeros, 4 ones. Then you alternate 2 zeros, 2 ones. And then you alternate every single bit, 0, 1, 0, 1, 0, 1, 0, 1. And you compute the whole thing. So for example, if you have 0, 0, 0, this will be 0, 0, 0. So you add all 3 zeros and that's 0, right? So that's, you can compute that easily. And so on and so forth. You can check it out yourselves, right? Okay, so I had the circuit and I built the Boolean expression, and I've got the truth table if you wish. Okay. Now, one remark, you see that this y is going to be equal to 1 when. Okay, did I write it here? No, I didn't. So let's just go back here. Look at this expression here. When does this light up to 1? These are pluses, right? So for a plus to be 1, you need one of these products to be 1, right? So that's when you know when y is 1. One of these 3 blocks has to be equal to 1, okay? Now, when is a product equal to 1? Well, each variable or primed variable in the product has to be equal to 1. This is the only way that a product is equal to 1. What I call a literal is a variable or negated variable, okay? So a product will be 1 if each literal in the product is 1. So the variables which are not negated have to be 1, and a variable which is negated, that variable has to be 0. Okay, so you see that this will be 1 precisely when either the first product is 1, which happens only if A, B, and C are 1, or the second product is 1. When will this happen? When A is 1, B is 0, and C is 1. This is the only way this can happen. And finally, the last one here, this will be 1 when A is 0 and B is equal to 1. C can be whatever you want, okay? So this is an important observation. If you reread if you got it, that's great. If you didn't quite get it, reread the slides, rewatch the video, think about what I just said, and you'll have understood something really important, okay? It's not hard, but you have to think about it, okay? Yeah. You know what? I think we're gonna. Okay. Are there any questions up to now? Comments?
None.
None. Wow. All right. Anybody else has none? Everybody's sleeping. Everybody's watching YouTube.
I mean, you could do that assumption again.
Me.
Yeah. Okay. All right. So, okay. So I had a circuit, I wrote down the Boolean expression, and I got the truth table from that, right? What about the other direction? If you give me a truth table, just a bunch of zeros and ones, can I build the circuit for it, right? So in a sense, we should be able to do that, right? So a long time ago, somebody said, okay, I'd like a machine that computes this thing. How can I do it? Well, here's what I wanted to do. Let's build it. Well, this is what we need to do, right? So the trick is these complete sum of products. So let's take a look at this. Okay, so I give you a table with zeros and ones. It could be anything. It could be just, I mean, of course, it could have it like a zillion variables. but you can just put any zeros and ones in there, and you want to build a circuit that will output that. Is it possible? Yes. So here's how we're going to do this. So here's a truth table, and I'm going to build a circuit that outputs exactly those values for y, okay? So obviously A, B, and C, these are all possible values for the inputs, but this is the values for the output, okay? So how do we do this? Okay, so first of all, I'm going to look at the triples for which y is equal to 1. So if you look at y, it's 1 on 0, 0, 0. It's 1 on 1, 0, 0, and also on 1, 1, 0 and 1, 1, 1. So I've listed all the triples for which the output y is 1. Okay? All right. So A prime, B prime, C prime, right? This is 1 when exactly if A, B, C are 0. There is no other way to make this equal to 1, right? If you input anything here, if A, B, C, one of these three is 1, it'll make the prime 0, and the whole product will collapse to 0. So the only way to make this product equal to 1 is if all three A, B, C are 0, 0, 0. Okay, now I'd like to do the same for 1, 0, 0. How can I do that? Well, take A, B prime, C prime. This will be 1 exactly on 1, 0, 0. This is the only input that will make this equal to 1. Okay? Then I do the same for 1, 1, 0. 1, 1, 0 will make A, B, C prime equal to 1, and it's the only input that will do this. And finally, for 1, 1, 1, well, that's easy. It's ABC, right? So ABC will be 1 on input 1, 1, 1, exactly. Okay? So for each of these 4 triples where y is equal to 1, I've found a product which is 1 precisely on that input. Okay? Now, what do I want? I want y to be 1 when it's one of these 4 triples. So either it's this one or that one or that one or that one. So what do? I take the or the plus of these 4 products. And it has to give me exactly what I wanted, okay? So again, when is this equal to 1? It is 1 if one of those 4 products is 1. And that's the only possibility. When are these equal to 1? We've chosen them to be 1 exactly, each one exactly on 1 triple, which are the 4 triples that I wanted to start with. Okay? So again, I look at my table. I look at where I want my output to be 1. I find a product which is 1 precisely on that triple, and I take the plus of these triples. This is, once you've understood this, it's not hard, but it's like a really fundamental observation, result, theorem. I don't know how to call it, but it's like super smart. Okay? So given any truth table, you can find a sum of products, which is complete, by the way. You see that these products all have all variables involved, and this Boolean expression will give you precisely the table that you were given. Okay? Now, once you have the Boolean expression, now it's easy to just draw the circuit, right? So I want an OR, so it's like think of the example that I gave you earlier. You have like this OR gate with 4 products coming in, right? So I'll leave it as an exercise, but basically you have your OR gate, you have 4 wires coming in, which are the outputs of your 4 ANDs, right? And these ANDs all have 3 wires coming in, which are either A or A prime, B or B prime, C or C prime. So you can mimic what you saw, the picture that I had a few slides earlier, and you'll see it's not too hard. I mean, the first times that you draw it, it might look really awful because your wires are going all over the place. But if you use a pencil rather than a pen, it should be a little better. You can fix things around, right? So again, what do we have? So I have another slide. Oh yeah, I'll get back to that in just a sec. So we have a notation for our OR, and NOT gates, which comes from engineering. It is very useful because it's very compact to write things down. We have drawings of circuits built from these, and we can go from a Boolean expression. Okay, so the Boolean expression, the table, it's easy to go from one to the other. The table to the Boolean expression, that's like the harder, trickier thing, which I've just done. And then we have the circuit and the Boolean expression. This is actually easy to go in one direction or the other. Okay, so now, yeah, one last remark I want to make is reducing circuits. I mean, we could do a whole semester on this, but we won't. This can be very, very difficult. I mean, there are some very deep questions today in computer science where can you reduce this? How much can you reduce the circuits? This is a very, very difficult question in general. But I want just to give you one little example because you might see this in some exercises. So here I have the, I think this is the first example I had earlier. Y is ABC plus AB prime C plus A prime B. And there's a way of reducing this as follows. So if you look at the first 2 products, you see that they have A times C in common. Obviously, the product is commutative, makes no difference in which direction in which order you write the variables. So ABC plus A prime AB prime C is the same as ACB plus ACB prime. You have this AC in common. You can factor it out. So the distributive law is valid. And as I mentioned, if you take B plus B prime, if you think about it just a few seconds, this is 1. That's always 1. So you can basically just erase that B plus B prime. So in this way, we could simplify the circuit. We get an equivalent Boolean expression and get a smaller circuit, which is AC plus A prime B. I will not drill you on this. I do not think there are any exercises directly related to that. And I will not test you on this. You will not see this on any tests, okay? If you go backwards, if you start with AC plus A prime B and you go back up with this technique, you see that, well, there's the A prime B that I'd have to fix, but I could just multiply it by C plus C prime. But how do you get a complete sum of products is same trick, but going in the other direction, okay? So complete sums of products are usually bigger circuits, but they're easier to deal with to find Boolean expressions. I'm gonna chat. That's a good question. Could you give an example of how we could be asked to use this in our future jobs? You want the real answer? I can't imagine ever and anybody ever asking you to I really don't see. Unless somebody's asking you, do you know how machines actually work inside to some extent? Otherwise, I mean, obviously most of us work at a very high level on machines, right? So no, you're not going to have to, but it's important. I mean, it's important to have some idea of what, I mean, how this thing is working, right? If you're going to spend the rest of your life working with machines, you don't want them to be your boss. You want to be the boss of the machine. And the only way you can do this is to have at least some minimal amount of knowledge of how it actually works inside. Um, I mean, computers have become extremely complex in the past few years. When I was a kid, I built my first computer. I ordered it by mail and I soldered the whole thing and it could play chess, but I built it, right? But today this is just nonsense, right? My first machine, when I bought it, it came, the the RAM was 1K. I'm not kidding. It had 1K of RAM.
Can I just ask a really quick question?
Yeah.
How much did you spend on the computer? Like, how much was that? Did that
At the
cost?
time, it
Yeah,
cost
I kind of want
me,
to know.
so that was in 1979. It cost me like 100 US dollars, which was a lot of money for me. Maybe 150 bucks. I don't know. Yeah.
That's not a lot of money in comparison to what it costs
No,
now.
no, but of course it didn't do that much, right? It was very, very primitive.
Still, a good computer would cost, like a grand at the minimum.
Yeah. But what this machine, I mean, in terms of what it did, as a computer, is just not comparable. I mean, it was even less powerful probably than calculators. I mean, it was much less powerful than calculators today, but it was simple enough for me to be able to control it right down to the assembly language. So I learned a lot by playing with that thing. But in the 15 years that followed, it just things in 20 years that just things exploded. And I mean, it's just, machines are now extremely complex. But in the end, in the basic principles behind it are the same. I mean, it's a circuit, and this circuit is built from these basic gates. Yeah. So that was the philosophical historical minute in the course. Okay. Any more questions? I'm done with the slides. Actually, I'm done with all that. So thank you. You're welcome. I didn't. I mean, I answered your question, but maybe not with the answer you wanted, or maybe it is. I don't know. Um,
Yeah,
yep.
yeah, sir. I was just trying to make sense on like combining the knowledge that we're learning from, say, Java courses and math.
Yeah,
But
they're far
besides,
away, eh? But that's what I'm saying. When you're learning Java, you're at an extremely high level, right? Java is a high level language, but what is actually happening when maybe you take I don't know if you're going to take an assembly course. Probably, I would think so. Maybe not, but sure, you could live without this knowledge, just like you can live your life without knowing anything about the biology of the human, uh, of your body, right? You might not.
but
Someone can
that's
live their whole
important
life
though.
without knowing what lungs are, what a brain is. You could, but it's much better if you do know ththese things, because when you
Of
get
course, yeah.
sick, right? When you get sick, you have some idea what's going on, and people are not going to. You're going to be a lot harder to fool, right? So it's a bit the same with the machine. You don't want the machine to control you. You want to be the boss of the machine. So of course, yeah, we could all learn a single language, programming language, and just be experts in that. But once the language becomes obsolete, so are we. So that's no good, right? So you want to be able to to have a better understanding of the machine, so you can. Now, how far does this knowledge have to be? That's another question. But yeah.
Yeah, out of curiosity, I have a question. Which programming language you think is the toughest?
I have no idea. I really have no idea. I no, I don't know. Really, I can't answer that. No, I don't know. For me, I mean, I'm a theoretician. For me, they're all the same. It's just, yeah. You should ask your programming teachers for that kind of question. Okay, I'm gonna stop the recording now. So I'll see you next time. I might record a little intro to this one because I forgot to do the beginning. Okay, I'll see you.